Okay, let me Control Alt Delete here. Maybe it's gonna go faster. Yeah, definitely the problem is Word, Microsoft Word. Oh well, I don't know. I do not know how long this thing is gonna last. Let me see. Oh, let me restart my computer because Word itself is not working. Okay, please hang in there. Don't leave. I'm gonna restart my computer, and when I come back, I will be able to get a better. Oh, here you go. See, Word is very slow. Let's see if okay, now it's working finally. And I'm gonna correct here. F3 is minus W. Okay, and then what I'm gonna do here, I'm going to write down like torque of 1, torque of 2, and I'm going to put a positive sign here in the last term, okay? And then whether it's positive or negative, you have to consult the drawings. And then that will be, I'll call that torque of W. I put the negative sign here because the force is downward, the weight is downward, the other two forces are upwards. The other two forces are preventing the board from keep on falling down. Okay, and so I'm just redoing the derivation in a more organized fashion. I don't need the net force here anymore on the left side. And I don't need the net torque here either on the left side. Look at that as a system of equations, right? I put an arrow here. We shouldn't have an arrow here because those forces are only in the one-dimensional problem. It's just an one-dimensional problem. Notice that I didn't put arrows here for the vectors. It's strange that not even my Control Delete is working. Okay, I can. Okay, see, come back. Let's see. I'm gonna quit Word, and hopefully everything, when I return, everything comes back normally. It's also possible that the problem is there in the cloud. By the way, can you hear me?
Yeah, we can still hear you.
Okay, good. I'm gonna close. Good. Let's see if it goes better now. For some, let me try Control Alt Delete again. Well, my Control Alt Delete is not working for some reason. Interesting. Control Alt Delete used to work. I gotta send my computer back to the guy who worked on it. Now let's see if the Word is gonna work now. Okay. Now let's see. Open the document. Yeah, now it's loading more quickly, right? Let's see. It's gonna continue like that. Yeah. Okay. So now it's going more quickly. That's good. Let me open the other document. It was just a matter of restarting the program, right? I didn't even have to restart the computer. Okay, good. Okay, and and let me remove the arrow from this force. Good. Now I don't need that on the left side. I don't need that on the left side either. Okay, so now we have this equation here with two unknowns. So we cannot solve this equation. We cannot solve this equation because we have, using this equation alone, we cannot solve a part of the problem, okay? Let's see if we can solve the problem using this equation here. That's what we did before the light went out. So the torque of one is going to be what? It's going to be the force of one, right? Force of one, and I'll call that distance of one from the point of rotation. Force of two, distance of two from the point of rotation. And then we are going to have W, the distance of W and W. Now, whether it's positive or negative, we have to look at the drawings. In order to look at the drawings, we have to get my PowerPoint right in here. Okay, and browse. I'm gonna go 2023 illustrations right in here. Now is the PowerPoint one that's okay, good. PowerPoint is coming. Just remember from the drawing, right? We are taking the point of rotation at the extreme left in the board. So the force F2 is the force F1 because we're taking the point of rotation at the extreme left. The torque due to the force F1 is going to be 0. The torque of force F2 is going to be counterclockwise, it's going to be positive. And then we have the torque due to the weight. The torque due to the weight is going to be negative because it's clockwise. Let's see if I can find it. It doesn't look like it saved my, yeah, unfortunately it didn't save it. Okay, so I'm going to have to do it all over again. Here you go. That's going to be the plank. That's going to be the force of the weight. That's going to be the force of the fulcrum around here. And then we have also the force of the of the bolt. F1, F2, and W. Here you go. F1, F2. No, that's not what I want. I want this one. I want the other one. That's what I want. F1, F2, and then we have to have the W as well. This other illustration that you see is from a different problem. Here you go. F1, F2, and W. Okay, we put the point of rotation right here. Consequently, the torque due to this force F1 is going to be 0. The torque due to this force F2 is going to be counterclockwise, so it's going to be positive, and the torque due to the weight is going to be negative. It's clockwise, consequently, it's negative. And here you go. I'm going to go the next step, like that. I repeat the first equation, even though we are not solving yet. I'm just repeating to keep there in our memory. And I go ahead, determine that the torque of this force 1 is 0 because D1 is 0, not because F1 is 0, but because D1 is equal to 0, the distance from the point of rotation. This force F2, we have the distance D2, and here we also have the distance DW, but it's because, oh, don't forget, we gotta put a negative here for the torque, negative here. Okay, and now we are almost ready to solve the part of the problem. Here you go. Like we did before. And let's both face what we do not know, right? Here you go. Both face what we do not know here. Both face, we do not know. And now that we have two equations and two unknowns, we know that we can solve this problem. Okay, and my F2, my unknown F2 becomes that. And then you have to substitute the numerical values right in there because we know the W, D2, and W. I'm gonna put it this way. Once you found F2, now you can find F1 from this equation. So again, I'm going to copy that and paste. I'm going to erase everything else because I don't need that. I'm doing a more organized fashion, right? That's what I'm doing right now. So I will substitute F2 in the equation above. See, that's the advantage of choosing the point of rotation properly. Because I chose the point of rotation at the extreme left of the board, this torque here ends up being 0. We eliminate an unknown from our second equation, and this equation here allows us to solve just for F2. Okay, so that's a very nice technique to improve your chances of solving the problem more readily. I substitute F2 in the equation above, copy and paste, and now I'm going to make it equal W minus, right? And I can erase everything else. Can I do better than that? Yes, I can do better than that. I can put W in evidence. Okay, and it becomes 1 minus dW over D2. dW over D2. That's what we have for that problem in there. We solved the problem. 11:35. Okay, I'm not gonna take attendance, but I will use the attendance that we had just before the light went out. Okay, but I saved the screen. Did anybody else came after the light went out? I don't believe so, right? Let's see.
Nobody really left. Everyone that's been here has pretty much been here the whole time.
And nobody showed up after the light show went out?
No, there was no prompts that anyone was trying to join.
Okay, I see here 7. That's good. And that what we have for this one, 11, let's see. That's one type of example using Newton's first law of motion. And oh yeah, I did the copy and pasted the table before. Before we go do something else, let me just remind you about the exam. No, let's see, syllabus. We have version number 7 there posted in Canvas. Here you go. We are doing this one right in here. Now we are not doing lab 6, right? Lab 6 is going to be postponed. Okay, right in here. Yeah, we're gonna end up doing only 7 labs, unfortunately. You know what? I'm gonna make this one lab 7, okay? So we do 2 different labs, only on one. We do 2 different labs on 2 labs on different topics. One in uniform circular motion and the other one on moment of inertia. Let's do it this way. Rotational motion, we're doing number 7. Okay. Lights out, huh? Lights out. No lights. No lights. And we go. That's what we have for exam 3, 5 through 7. No, it's gonna be 5 through 7. Lab 3, 4, and 5. Lab 3 is correct. Report for lab 3 is corrected. 5, 6, and 7. I'm gonna boldface this one. Remind you. What else can we do? Okay. We're gonna work on Newton's second law of rotation. Newton's second law for rotational motion, okay? And we're going to okay, what we did before was the case for rigid body in static equilibrium. But what if the rigid body is not in static equilibrium, right? What if the rigid body is not in static equilibrium? Then we must apply Newton's second law to rotational motion. Okay, what we have, what's the procedure to do that, the derivation process. To find out Newton's second law of rotational motion, first apply it to a point particle undergoing rotation. Okay, we consider a point particle in the whole mass. The whole mass is M, has a mass M. And assume that the object is made of several point masses. And also is subjected to, then each point mass is subjected to a tangential force. That's why it is accelerating. Okay, so consider that if we have something like that, an infinitesimal mass part of the object. Let's see if I can get it drawing here for you. It would be something like that, okay? So here you go. Here is my infinitesimal mass. It's the object is accelerated this rigid body is accelerated. Consequently, it has a tangential acceleration. If it has a tangential acceleration, each of one of those masses must have a force that's propelling it to accelerate in the tangential direction. And then we can write the equation for each of those little point masses as being force, tangential force in that little mass is equal to mass times acceleration. Okay. And now we also have to look at the torque applied to each one of those point masses. The torque applied to each one of those point masses is going to be the tangential force that's producing the torque times the radial distance of that point mass, that infinitesimal point mass. We substitute the tangential force equation right in here, we get something like that. And then let's not forget the conversion between tangential quantities into angular quantities. Remember that, right? And look what we get. We get m alpha r squared. And we rearrange the term to show something like that, mr squared times alpha. What I call the angular mass is exactly this term, but let's not forget, right, that this distance r may be different for different positions, for different points along the, throughout, not along, but throughout the rigid body. Okay. So this term here is what I call the angular inertia. Okay, mass is in reality linear inertia. Let's call m as the linear inertia of an object, right? Of an object. That's what mass is all about. It's a measure of the inertia of an object, how difficult it is to change its velocity. The larger the mass, the more difficult it becomes to change its velocity, to change its inertia. So if m is the linear inertia of an object, okay, m is the linear inertia of an object, then this term here is going to be the angular inertia of your object. This angular inertia has a name. We call it moment of inertia I. Okay, so we are going to write down my moment of inertia. I becomes mr squared. Okay, so here you go, going back to this. So this infinitesimal mass must have a different moment of inertia than this other infinitesimal mass. Even if the masses are the same, the moment of inertia of them is going to be different because their radius, their radial distance from the axis of rotation is different from the other one. Okay. And now we go ahead, you know, if we can here write our net torque as being I times alpha. Okay, and compare that with Newton's second law. Linear inertia, angular inertia. Linear acceleration, angular acceleration. But let's not forget, you know, this r here can change from one infinitesimal mass to another. Consequently, my net torque can be rewritten, or even my moment of inertia can be rewritten as in terms of a summation. Right in here. Where the mass has a subscript and the r also has a subscript. subscript I. And this I goes from 1 to n. Okay? To n. And I can here write my net torque as being something like that. The angular acceleration throughout the whole object is the same. And because of that, I'm going to put a parenthesis here. The angular acceleration doesn't have to be inside the summation sign. Angular velocity is the same throughout the whole object. What is different is the linear velocity of each infinitesimal mass there inside. Okay? Now, let's see, 11:45, 47, we have 15 more minutes to go, right? If you want to calculate the moment of inertia of several point masses rotating about a fixed axis, okay? Assume that the point masses behave like a rigid body, right? It becomes easier to calculate the moment of inertia, right? Moment of inertia. Moment inertia. And let's do, I want to do an example here. 4-point masses. Let's see if I have it. Let's see here. Hopefully I have an illustration here. There's a very nice example. If you don't have it, I will have to, okay, I'll have to make a drawing. I have to make a drawing. It's think about the baton. Example. Example. Moment of inertia of a baton with baton with n, with 4-point masses connected, 4-point masses of known values, 4-point objects, 4-point objects of known masses connected by a rod of negligible, connected by 2 rods, not a rod, but 2 rods of negligible masses. Okay. So I'm going to do right in here. Let's see. I'll take advantage of this one. I don't need them anymore here. Erase, erase. Okay, here's my rod. I'm going to come out with another rod. Oh, not this one. Rotate it, right like that. Those rods have different sizes. View. Guys, grid line. Okay, this one seems fine, right? Yeah. And this one, yeah, good. Let's centralize them. And we have those point masses here at the edge. another point mass. A little bit more. Yeah. And I'm going to put this one here and the other one there. So let's see, I'm gonna make things easier for all of us. This is gonna be M1. This is gonna be M1, non-masses. This is gonna be M2. This is gonna be M2. And also non-distances from the center of the baton. Here is going to be here is going to be B. Okay, B here, B here, from the center. And the other one is going to be A, and A. That's going to be here, B, okay, B. 4-point masses. So this problem, we can do two different problems here. One more difficult, the other simpler. Okay? Two problems. You know, find the moment of inertia if this baton is rotating about this axis here. This vertical axis that comes out of the board, that comes out from the my screen. Here you go. And position. These are all one format shape. You know, line. I'm gonna put a. Here you go. Like that. It's rotate like that. The axis is this one right in here. I'm going to make a smaller sphere so I can put at the very center. Right here. That indicates the vector velocity, angular velocity of the baton. Okay? We're going to do this problem, and we're going to do a problem in a different problem in which the axis is not going to be this one here, but the axis is going to be the axis of rotation is going to be this one here. Okay, here you go. Two different problems. Same configuration, but different axis of rotation. Find the moment of inertia for this configuration. Find the moment of inertia for this configuration. Okay. Here you go. Like that. Into front. Like that, okay? Bring to front. I want to bring this one to front. Yeah, okay, now we got it. Now we got it. By the way, this problem here is easier than this one. We're going to do the more difficult one, okay? So just by orienting the axis in a different way, the inertia of the rigid body changes, okay? That's what the lesson that you have to take from this problem. We're running out of time, right? Only 3 minutes to go. Okay, so I'll try to set it up as quickly as I can. Solution. Okay. See PowerPoint drawing. Okay. The first one, the moment of inertia, is very straightforward. Okay. So here we go. Is going to be M1 R1 square, M2 R2 square, M3 R3 square. Right? M2 R2 square. Here's M R1. M3 square. M4 square. M4 R4 square. Okay, I don't need the summation anymore. It's kind of unfortunate notation, right? So let's see if I can fix that. Instead of M1 and M2, let's put it here. M1 and M3, right? So the notation now is, M3. And we do the same here, M3, M3, M1, M1. Okay, now the drawing is one more minute to go. M2 is equal to M1 and R2 is equal to R1. M3 is equal to M4 and R4 is equal to R3, right? And now we can get a result that was just like that. One more. Okay, that's the moment of inertia. And here the R1 is what? R1 is A. R1 is A. R3 is going to be B. Just like in the drawing. Okay, and we can repeat that for the other axis. Example 1, axis pointing towards you. Axis running along masses M1. Okay, running along masses M1. Okay, now in this other situation, here you go. Axis running along masses M1. In this situation, the distances of these masses from the axis of rotation is going to be 0. Okay, it's going to be 0 because they lie exactly at the axis So what we have here for those two terms is going to be 0, 0, and 0. And what you're going to have for the other two terms is going to be b squared and b squared. And we end up with 2m3b squared. So look what happened. Just by changing the axis of rotation, we get a different moment of inertia. So next time, okay, 1202 already, right? Next time I will show you how I'm not gonna do it how to calculate because we cannot do that. Yeah, I'll show you how to calculate the moment of inertia of some uniform distributions. Okay, like a ring, a sphere, not point masses, but distributions, not uniform distributions. How to calculate of continuous distributions of mass. Okay, continuous distributions of masses. Okay, so we can stop here now, and I'll save this document and I'll upload it later on. Any questions? So I see you on Monday. Okay, till then. Stop sharing and click on phones. How do I stop recording? Recording. Stop recording.